Dear students, welcome to a new video for the sampling course. We will use in this chapter we will give the percentages of the population. Sometimes we wish to estimate the total number or the proportion or the percentage of units in the population that possess some characteristics or attributes, or fall into some defined classes. Many of these results regularly published from censuses or surveys are of the form, for example, numbers of unemployed persons, the percentages of the population that are native born. The classifications may be introduced directly into the questionnaire as any questions that are answered by simple yes or no. In other cases, the original measurements are more or less continuous, and the classifications is introduced in the tabulation of results. Thus, we may record the respondent's age to the university year, but publish the percentages of the population aged 60 or over. Notations that we suppose that every unit in the population falls into one of the two classes C or C complement. The notations are in the following table, where the number of C units is the population, capital A, and sample is small a. Although the proportion units in the C is in the population equal to P equal to capital A over capital N, and the sample P small equal to small a over small n. The sample estimate of capital P is small p, and the sample estimate of capital A is n times p, or Na over small n. The statistical work, the binomial distribution, is often applied to the estimates like A and B. As will be seen, the correct distribution for the finite population is the hypergeometric, although the binomial distribution is usually a satisfactory approximation than the hypergeometric. Now we will move to the other section, which is the 3.2 differences of the sample estimates. By means of a simple device, it's possible to apply the theorems established in the second chapter to this situation. For any unit in the sample or population, define yi as 1 and the unit in C is 0. If it's C dash for the population of the y, it's clear that capital Y will equal to the summation of yi from 1 up to n, which is equal to capital A, and hence y power will equal to summation of yi over capital N, which is equal to capital A over capital N equal to P. Also for the sample, the y power will equal to summation of y small I over n small, which is equal to small a over a small n equal to P. Consequently, the problem of estimating the A and P can be regarded as that of estimating the total mean and population of a population in which very yi is either 1 or 0. In order to use the theorems in chapter 2, we first express s square capital S square as small s square in terms of P and P. That summation of yi square equal to capital A, which is equal to capital M multiplied by P, and the summation of I square small for the sample equal to small a, which is equal to n times P. So S square, the variance, will equal to summation for yi square minus n times y power square over n minus 1. Here, 1 over n minus n equal to n of times p minus n times p squared, which is equal to n over n minus 1 multiplied by p times q, where q is equal to 1 minus p. Similarly, we get the small s square equal to n small over n minus 1 times p times q, where q is 1 minus small p. The applications of the theorems 2.1, 2.2, and 2.3 to the population give the following results for the simple random sampling of the units that are being classified. Theorem 3.1 states that the sample proportion P equal to A small over small n is an unbiased estimator for the population proportion P capital equal to capital A over capital N. And the other theorem, which is 3.2, that the variance of the proportion Vp equal to expectation value for P small minus capital P all square, which is equal to S square over N times capital N minus N over capital N, equal to PQ over N times N minus N over N minus 1. So we can, this results if P small and P capital are the sample and population percentages respectively falling into classes C, there were that 3.6 continues to hold for the variances of E. Another corollary that the variance of A hat equal to N capital times P, where the estimated total number of units in class C is variance for A hat equal to N square PQ over N times N minus N over N minus 1. The theorem 3.3 also stated that an unbiased estimator for the variance of P derived from the sample is variance for small p, V for small p, where is S squared small for P equal to N capital or minus N over N small minus N minus 1 over times N capital, all R times P times Q. We can prove it simply by using the corollary of the theorem 2.4 as shown that a variance of yi is an unbiased estimate of the variance of the sample mean y par, where the variance y par equal to S squared over N times N capital minus N over capital N. So the proportions P take the place of y par, and in 3.5 we showed that S squared equal to N over N minus 1 times PQ. Hence, by substituting, we get variance for P equal to S squared P equal to N minus N over N minus 1 times MPQ. Now, we got that it follows that if any n is very large relative to small n, so that APC is negligible, and an unbiased estimate of the variance of P is PQ over N minus 1. Remember to check it's finite or infinite first before substituting in your equation. The results may appear puzzling to some readers, since the expression PQ over N is almost invariably used in practice for estimated variances. The fact that P times Q over N is not unbiased, even with an infinite population. So we can get to this result that unbiased estimate of the variance A hat equal to capital N times P, the estimated total number of the units in class C in the population, is variance A hat equal to S squared NP equal to the N capital times N minus small n over N minus 1 times PQ. Thank you.